In this video, we're going to be exploring the remainder theorem when it comes to polynomial division, but also tying in polynomial long division with synthetic division, the beginnings of. So we say, let's let f of x be this polynomial function right here, this third degree polynomial function. And what we want to do is we want to use long division essentially to divide this by x minus 2 and then write the quotient and then talk about the remainder. So let's take a look at this instance right here. So we say that this is our dividend, and it's the thing that goes inside of our array. And I notice that I have an x cubed, an x squared, an x to the first, and an x to the 0 term here. So we don't have to fill in any zeros. We have every term that we need to have here. So minus 2x squared. We're going to take this plus 2x to the first minus 5. And we'll divide all this by our linear divisor, which is, I call it a linear divisor because it's a first degree divisor, but we say x minus 2. So if we're going to divide this out, so remember long division, we have a division algorithm, but it's basically does McDonald's sell cheeseburgers, but this stands for divide, multiply, subtract, carry down, and then begin again. So begin again. And so these are the steps we're going to take as we go through this long division right here. So we say, okay, so divide. What can we take times x to the first to get 3x to the third? We could take it times 3x squared. So 3x squared times x to the first is 3x to the third. 3x squared times a negative 2 is a negative 6x squared. And what we're doing is we're subtracting all of this. So subtract it all, parentheses around it. So we're going to add the opposite instead. And instead we get these to cancel. We get a positive 4x squared. And then we'll carry down our 2x. And we'll begin again. We say, now, how many times is x squared going to 4x squared? You know, what could I take times x squared to get 4x squared? Well, we'd have to take it times a positive 4 and another x. So we say, well, 4x times x is 4x squared, but 4x times a negative 2 is a negative 8x. So we're going to subtract now all of this. So add the opposite. So these cancel. I get left with 10 x's. We'll carry down our negative 5, and we'll start up again. So now I say, well, how many times does x go into 10x? Well, what could I take times x to get 10x? And we can take it times a 10. So I say, we'll put a 10 here. 10 times x is 10x. 10 times a negative 2 is a negative 20. And so since we're taking all of this away, we'll go ahead and add the opposite here. So we'll make this negative and this positive. And so these cancel, and we get, looks like a positive 15 here. So this remainder thing right here, remember, we have to put this back up here. So we say plus 15 all over x minus 2, which is the thing we were dividing by. So this thing right here, what I want to do is I actually want to ask some questions about this. So I say, well, let's use synthetic substitution to evaluate f of 2. Recall that when we do synthetic substitution basically said, look, I wanted to go find like f of 2, what does this equal? And it was a way of doing this without having to go plug in a 2 everywhere you saw an x. So the way we did this was we took the coefficients from this, so like the 3, the negative 2, the positive 2, and the negative 5. 3, negative 2, positive 2, and negative 5. We put those in this array, filling in any zeros if we need to. And then this x value is what we threw out here, so we say x equals 2, for instance. And so the way this works is we carry down this leading coefficient. 2 times 3 is 6. Add vertically, so negative 2 plus 6 is 4. 2 times 4 is 8, and 8 plus 2 is 10. We say 2 times 10 is 20, and 20 minus 5 is 15. So this thing right here, this is our f of 2. So we say go find f of 2. We say f of 2. I mean, I would write in the section of f of 2 equals 15. But it says, how is f of 2 related to the remainder we did in this last problem? And what I want everybody to notice is this remainder. You can see up here, we got 3x squared plus 4x plus 10 plus 15 over x minus 2. This thing right here is actually, if we want to consider it, this is the remainder of a division problem. Okay. So we say, how is f of 2 related to the remainder? It's the same thing. So not only is this last number the y value of this x value, it's the remainder that you get when you take, say, this polynomial here and you divide it by x minus 2. So speaking of, it says, what do we notice about the other constants in the last row of the synthetic substitution? What I mean here is this 3, this 4, and this 10. If I go back up here and I look at the quotient, it looks like we get 3x squared, 4x to the first, and then 10x to the 0, where 15 was the remainder. So really what we've just done right here is what we've called synthetic substitution. But the profound thing is this. When you do synthetic substitution, this last number right here not only represents the y value when you plug this x value in, but it's also the remainder you get when you synthetically divide this original polynomial by x minus 2 in this case. And we put a positive 2 out here, I'm aware of this, but when we divide it by this is what we're dividing by. So here's what we want to recognize before we go into this next activity. But it says in the last activity we discovered that f of 2 is the remainder when we divided f of x by x minus 2. So we took really this f of x divided by x minus 2, and we got the remainder was our f of 2 value, which is profound. So we say this result can be generalized in the remainder theorem. The remainder theorem basically says this: if a polynomial, some polynomial, if we divide it by, say, x minus k in general, we divide it by x minus 2 up here, that's what we're dividing by, then we say the remainder, this last number right here, is actually equal to f of k. So again, in the last example we just did, we said f of x was some function, and we divided it by x minus 2. So this would be like our x minus k here, right here. This is our factor. And we say that really the remainder is equal to f of k. So in this case we'd say f of 2. So k is actually backwards from what you see here because of this negative in front, but we found f of 2 is the remainder, okay? So I say we should also have discovered that the synthetic substitution gives us the coefficients of the quotient. So these right here, I want to make sure that we write this too. These are the coefficients of our quotient of, and I'm going to write the quotient, f of x, which we had some f of x, divided by x minus 2. Okay, and this is the remainder right there of that quotient. So since synthetic substitution actually does this, what I can tell you is this, and we'll use this more in the next video, but we say synthetic substitution is sometimes called synthetic division. And the reason why is because it can be used to divide a polynomial by an expression of the form x minus k. So now the last thing I want to make sure we would note here on this video is this. We say x to the first power minus k. So this is itself its own polynomial, but we say it's a first degree polynomial. And we also want to call it what it is, which is a linear divisor. So the thing we are dividing by is to the first degree. Anything the first degree is linear, okay? So basically, if you're ever going to take a polynomial and divide it by a linear factor like this, which is of the form x minus k, then we would say really then what we're dividing by is that factor, and we could just plug in x equals 2, positive 2, out here, and we'll actually get the quotient right here, and we'll get the remainder right here. So in the next video we'll put this to work.